Chemistry is largely about electrons, and I'll say it 1,000 times, probably almost as much as I'll say nature favors low system energy. So it behooves us to understand a little bit more about these electrons. One question comes up right away if you think about it. If the nucleus is positively charged and the electrons are negatively charged, and opposite charges attract, how come the electrons don't go collapsing down into the nucleus? Well, the obvious answer is that they have energy. They have kinetic energy, the energy of motion. And it is that energy that keeps them from succumbing to the pull of that nucleus and keeps them in orbit, if you want to use that word, around that nucleus, the marble in the baseball stadium. Chemical reactions involve the interaction of electrons. And as a result, then, we're interested in the energies of those electrons. A lot of the properties of elements relate to the energy of the electrons and the configuration of it and the shape of it. And this chapter here begins to outline some of those ideas and makes the relationship between measurable things and that energy, that all-important energy. We need models to do that. And 100 years ago, the wave model was a very popular model for lots of different phenomena. And obviously, scientists could watch waves in a pond or water travel and measure their properties. And this whole idea of the propagation of some energy in this form had a lot of different uses. And here then, sketched out briefly for you, is sort of the traditional wave model of light, light being a form of electromagnetic radiation. The properties relate to the length of the wave, wavelength, and the amplitude of the wave height, and the frequency of the wave frequency then being the number of peaks that pass at a certain point in a given amount of time. You've all stood, I'm sure, on a pier or on the beach or whatever and watched the waves come in. This idea then of their height, their wavelength relates to how far apart the crests are, and the frequency then would be the number of waves that pass a certain point in a given amount of time. Obviously, if we're dealing with light or other forms of electromagnetic radiation, the scale is dramatically different because all electromagnetic radiation moves at the speed of light, some 3.0 times 10 to the 8 meters per second, and hence the properties, macro scale properties, what we observe, a little bit different than what we observe when we watch water waves, which are, of course, moving very, very slowly. But these same properties are important. The wavelength corresponds then to the type of radiation, the amplitude to its intensity, and the frequency is governed by the wavelength, in as much as frequency and wavelength must always multiply together to give us the speed of the wave, which in this case is always the same, 3 times 10 to the 8 meters per second. Go out there in the internet land and find a good-looking electromagnetic spectrum. Here then, one that you probably can't read on this little song and dance, but nevertheless it isn't enough for me to talk a little bit about what's going on here. Up at the top are the two scales, wavelength and frequency. Remember, the product of wavelength and frequency is always equal to c, the speed of light. And by that, you can figure out that very, very short wavelength waves have a very, very high frequency, and long wavelength waves have a very low frequency as a result of the necessity for the product to always equal a constant. You see some of the things perhaps you've heard about, or different types of radioactive, sorry, I keep saying radioactive, electromagnetic radiation. It's a continuum, of course, but we group chunks of it into categories and refer to them as microwave radiation, radio waves, UV radiation, and then of course X-rays and gamma rays, which you probably heard about, but hopefully have never experienced. And nestled right in here in a very, very, very narrow range is the visible portion of the electromagnetic spectrum, the part that we see as color. And should you ever get kidnapped by aliens, and they ask you what the sensitivity of the human eye is, you would respond that we can see wavelengths between about 400 and 700 nanometers. Nanometer, of course, a prefix on our base unit, the meter. 1 times 10 to the minus 9 meters. And so there are the familiar colors to you. Any wavelength, frequency, right? They're always related. Outside 400 to 700 nanometers, we can't see, although certainly that radiation is out there, and we can either feel it in the case of UV radiation and intense heating, or perhaps detect it by using various receivers, but it is essentially all part of the same basic phenomenon. One important point that you can deduce from this is that the shorter the wavelength or higher the frequency, the greater the energy of the radiation. Hence, X-rays and gamma rays, very, very high frequency, short wavelength, radiation is high in energy, whereas the long wavelength, low frequency radiation contains a lot less energy. Won't go into that in any great detail here, except to point it out. One of the reasons that you shouldn't get a lot of X-rays is that the energy content of those is very, very high, and it can interfere with your bodily processes, cell division, and all other cool stuff. Around the turn of the century, believe it or not, the very, very useful wave model of light began to show some cracks in terms of its ability to understand the increasingly small atomic world and atomic phenomenon. And what this led to ultimately was the development of another model of light that related to the particle behavior, particle-like behavior. This, you could go out there and Google wave-particle duality and be treated to, I'm sure, a number of explanations and presentations of what this conundrum represented. But for us, we're still focusing in on those electrons, and so we can sort of resolve this by thinking about these electrons and what they are. And the particle theory, particle model for light then essentially suggested that these phenomenon, electrons, let's just call them that, exist as discrete packages of radiation or light, and only certain energy values could be attained by those electrons. The wave model implies that any energy is possible, and the particle model of light essentially backs away from that and says, no, energy has to be quantized into discrete packages, and this went a long way to helping us understand the behavior of atoms and the electrons they contain in a number of experiments that we'll see. One of the famous experiments had to do with the photoelectric effect, and Einstein was involved in this research, as well Max Planck, who was an early leader in this transition between thinking about light and energy as waves and thinking about it as a particle. The photoelectric effect, quite simply put, had to do with the fact that metals have electrons that are relatively loosely held. These are the same electrons, by the way, that allow metals to be malleable and ductile and to conduct electricity. These mobile electrons, loosely held to the nucleus, can move readily, and as a result, many of metals' properties are related to the behavior of those electrons. In any event, the idea here was that different metals with different energy levels for their electrons responded differently to different kinds of radiation, and whether or not the electrons were kicked off of the metal and detected had to do with the frequency, not the intensity, the frequency of the radiation. And there was a threshold frequency that was required in order to kick off the electrons. And once that threshold frequency was attained, the electrons were readily kicked out of their atoms and detected here in this measurement device. But if the frequency was insufficient, no electrons were ejected. This has often been likened to the idea of a soda machine or some kind of vending machine where the item costs $1. And if you put a dollar bill into the vending machine, you get your soda. But if you put in 4 quarters, you don't. That is to say, in this new model of the atom, you can't add up energy. All you can do is deliver it in certain discrete quantities called quanta, the plural of quantum, quantum mechanics then being this new model of the atom. And this photoelectric effect then was readily explained by the energy in radiation being quantized into discrete levels. And if there was sufficient energy to kick off the electron, it happened. And if there wasn't, then it didn't get emitted no matter what the intensity of the radiation was. This can be quantified and in fact is embedded in an important physical constant, Planck's constant, which relates energy to the frequency of the radiation through a constant, as you've seen before here, the units being contrived to be whatever they need to be to transform 1/seconds into energy terms. This relationship then used to assign energies to various frequencies of electromagnetic radiation. Here the pH stands for photon. You may not know, but it is in fact a real word and was the word associated with the particle of light that corresponded to the particular frequencies. And here just a simple multiplicative relationship. HV, where H is of course the constant that Planck derived. And we can go then, as we will in class, using a few examples, from a wavelength, in fact from a color, through a wavelength to a frequency, and then frequency itself multiplied through using Planck's constant, giving us a energy. Obviously the energy of one photon is very, very small, but obviously a single photon is a very, very small part of these phenomenon. And so typical energies then for photons of visible light in the range of 4 × 10⁻⁹ joules. The idea of where are those electrons has not surprisingly occupied a lot of time for everybody because it's an important idea. And one of the things that we'll see in just a few minutes is that the early portrayals of the atom were not especially accurate, and that the energy levels of these electrons exert a very important influence on the chemical behavior. And I think we'll pick it up here in the next video.